And so I'll be utilizing embodiment to evolve robust classifiers that utilize vision. Current work in deep neural networks was found in a recent paper to have some kind of issues with adversarial, adversarial kind of evolution of pictures that kind of fool the classifiers in thinking with 99% or more certainty that these images contain the classified objects. So whether it's the white noise containing a cheetah or a robin, or those weird patterns containing a king penguin, it kind of shows that the that current state-of-the-art algorithms for classification still pick up on features that we as humans would not pick up on. So to kind of like show in how that works in a very simple example, and how these visual systems sometimes tend to overfit the training set, imagine you have a robot here with 2 arms and a camera right on the little red block, and it's looking into the screen. If it's trained just on the blue blocks, or the blue cylinders, and is tasked to classify their size, when it's provided a purple or pink cylinder in the middle, it's never had that sensory experience before, and so it's not going to know how to classify that object. And perhaps it's going to make a mistake or make a guess, but it's probably not going to know what to do. So we're wondering, maybe the arms of the robot can help and can have some sort of useful effect for the robot. And so in cognition, the field of cognition, there's kind of 2 sort of competing perspectives. There's this embodied cognition that takes that the source of our brains is just data, and if you just provide a robot enough data, it will eventually come out with an intelligent mind. And then there's the embodied cognition approach, which posits that a body is necessary for at least seeding cognition, whether it's in a human being or an organism, or a robot mind. And so if you use active categorical perception in a robot like this, active categorical perception, or ACP, being categorization through action, we see that regardless of where an object starts off in front of the robot, the act of grabbing and grasping the object on using an evolved controller kind of ignores the initial position, or spurious feature of the problem, and kind of reaches the same final position regardless of the object's position, but different sized objects are going to reach different final positions. And so it kind of shows that because ACP naturally kind of, in the grasping motion at least, kind of gets rid of or helps ameliorate the problem of overfitting. And so the motion itself is helping us with the problem. So vision has a propensity to instantly see the scene and just try to learn from that. So it has a propensity to memorize. Whereas proprioception, because it needs to manipulate the object, has some sort of advantage in terms of having to just do stuff with it, and that we think could be helpful to visual classifiers. And so we're wondering, so if we want to evolve robots to check this and see how robots with vision and robots with feeling evolve, we're going to use evolutionary robotics. So we're going to use an evolutionary algorithm. For instance, in our case, we use CMAES to involve the robot brain, and then give it a task, throw out the bad scoring agents, and then mutate, in this case, the really good performing agents, and then create a new population over and over again until we get high scoring on the training set, at least, robot. Okay, so how do these robots work specifically? Our neural network is a recurrent neural network, and on the inputs, we have the joint angles. That's going to be proprioception of the active categorical perception of the robot. And these joint angles are going to take some kind of value. For instance, the first value might be the elbow of the robot, or might be one of the shoulders, or the other elbow. So say we take this joint angle here. That's the elbow of the robot. Depending on how open or closed it is, it's going to have a certain value. And so throughout a simulation of the visual robot, as it goes to hug, it's going to get a certain information that then tells it to how much it should continue opening or closing its arms through motors, or what the guess of that robot as to the object size is. And so the guess neuron over time is going to start off at some value, and then depending on the evidence presented to it through its perception of the scene is going to settle on a big object and say 0.5. We think the object is really big because the arms are really far apart. Or it's a small object, negative 0.5. The eye neuron thinks like it's a small object, our arms went really close, and we're guessing it's a small object. And so over time, we're going to evolve these brains using our evolutionary algorithm. And we did this for 10,000 fitness evaluations over a couple different training positions for each brain. And we received fitnesses so we picked the best brain during the training phase as to its training fitness. And then we tested it on all these various positions in front of the robot and got a testing fitness. And so for one of these, for instance, the V4 example, which is this one right here, a value of 0.0 would indicate that the tested brain on all these positions perfectly categorized the object, whereas a value of about 0.5 indicates it's just guessing, it doesn't know. And so we then proceeded to do the same thing for a couple different scenarios, horizontally placed objects and alternating placed objects, so the two object sizes wouldn't be concentric on each other. And we also tried it for increasingly more data on the training set, so either 6 objects or 8 objects. And then we did the same thing with vision. Instead of our inputs being the joint angles, we used eyes. And our eyes are a little different than humans' eyes work. There's 4 eyes. You kind of see the line series projectors overexposing this a little bit. So each of these eyes is basically left middle, or left, or middle left, middle right, and far right. And so depending on what the eye sees in a certain set of degrees, it's not exactly vision, but a distal sensor, so sonar essentially. So the more inclusion, the closer the object is to its eye, the lower the value. The further it is, the higher the value. And what we found is that when we compared using a two-tailed t-test of the test means for 100 evolutionary runs of each proprioception vision for each of the 9 environments, we found that in 8 of them there was a statistical likelihood of a p-value below 0.05, and in 7 of them below 0.01, that proprioception did a much better job of generalizing on the test data set than vision did. And so this indicates to us that something about the way proprioception is working is generalizing more. And so we think this is because of movement. And so in our 9 environments, we found that except for A8, in all the other ones, vision has much less movement. And by movement, we mean we compare the initial position of each of the objects to its final resting position in an individual simulation. And we find that the vision-based, so the right bars, the green bars, tend to evolve characteristically less movement than proprioception. And in 4 of the examples, 4 of the environments, vision tends to very often evolve no movement at all. So it just memorizes the training scene and just doesn't choose to do anything with it at all. And so we were thinking, how can we move from proprioception to vision? So in the field of developmental psychology, there's the idea that perhaps one of the ways that human babies learn to see is by first feeling objects, grasping them, and bringing them to their face. And perhaps the motions, those kind of motions, help slowly teach the baby and develop its vision to be the level of our human adult vision and be able to categorize and judge objects from a distance. So we're wondering maybe we could do the same thing for the robots. So our fundamental question is, can learning to feel speed up learning to see? And we're particularly going to do this using sensor scaffolding. So the 2 sensors that we have are proprioception, the joint angles, and we're going to have vision, which potentially in modern cameras is thousands of pixels. But in our case, we're going to use kind of a one-dimensional horizontal ray of 36 rays that are then split up into each of the 4 eyes. And we're going to work off of 2 types of lifetimes, which are the different kind of time scales. And so if you're not familiar with biology, this can be really confusing. These words can be confusing. So there's ontogenetic timescales, which is the development of an individual robot, or one single simulation. So this would be like one individual human life. And so in this case, it's a simulation of a hug, for instance. And then there's phylogeny, or the phylogenetic timescale, which is the evolutionary history of these robots. So the one individual complete run, an evolutionary run. And so it's a randomly initiated CMES all the way through. And so in the scaffolding, our first approach in a series of increasingly gradual scaffolds is we're going to call the naive scaffold, where halfway through evolution we're going to decide, you know what, this robot, this species lost its ability to understand what's happening in its joints, but is instead going to develop eyes. And so halfway through the vision, halfway through the first half of evolution is just going to use these joint angles for each of the input neurons, and then it's going to be completely shook up and instead use eyes as its input in the second half. And so in some sense, it's being primed by the proprioceptive time step. And we found that when we then tested this using just vision, we found that in 3 of the environment positions, particularly the ones with fewer training examples, that the testing fitnesses into testing errors were lower than when it was just trained and tested on just vision. And so that's some progress. Then that tells us that there's something about motion and active categorical perception that then conveys certain information to the robot that then leads to more robust classification in these and generation of more robust controllers. So we then tried 3 more scaffolds that used a more gradual approach over the phylogenetic or evolutionary timescale, where for the first 30% of evolutionary time, it was just touching and just proprioceptive ACP. And then we had a mixing phase where the component of vision was linearly increased while the contribution of proprioception was linearly decreased until the final 10% where it was just trained on the vision inputs. And from that final 10%, we picked the best, highest fitness training robot controlling. And so our first of these scaffolds is known as swapping. And so what we did essentially, we initially, for the first 30%, we started with the joint angles, and then we said that in the mixing phase, through an individual life or on the ontogenetic timescale, we're going to choose to swap and basically turn on the eyes of a robot late into its life. And so initially, very late into its life, it's going to swap from proprioception to vision, and then over evolutionary time, as the mixing phase continues through the 60% of its time that it's mixing, the swapping point is going to move further and further to the left until the robot from the very first time step of its individual life is just seeing. And when we tried this, we found that so in this case, it was also tested on just the vision as its inputs, we found that pretty much the same results as naive scaffold. That in some sense, the swapping is still too jarring on the neural network and in some ways affecting the hidden neurons too much. And so we tried another scaffold. And the next one was a melding scaffold, which is our essentially averaging. And so weighted averaging. And so same thing, first 30% was just proprioception, ACP. Then we did melding where through the phylogenetic timescale, the contribution to the input was mostly proprioception initially. So 95% of the value of the neuron was what the joint saw. And then the final 5% was what the eye saw. And then over phylogenetic time, these lines moved closer and closer together until they flipped, and it became entirely what the eyes saw and nothing what the arms felt as the inputs. And then the final 10% again was just what the eye saw. And we found that, wow, in 5 of the cases, environments, the controllers evolved more robust and generalizing behavior when compared against what was evolved using the pure vision trained and tested controllers. So progress, so something about smoothing it out is helping. So, but in this case, it's only, I think, a 0.05 or 0.01, a p-value of 0.01 as opposed to these being much lower. And so we then used a sigmoidal scaffold that changed over both phylogenetic and ontogenetic time. And so, same thing, first 30%, proprioception, then at some point, the robot became more and more decrepit in terms of its feeling and kind of opened its eyes. And so the contribution of vision increased. And then over phylogenetic time, these intersection point moved farther and farther left until it's disappeared. And from the very beginning, it was nothing but vision. And again, same awesome results. In 5 of the examples, there was progress. And even as we gave it more training data, it seemed to work in this case. And so our results basically are that proprioception generalizes better than vision, in large part because of the movement. That something about moving around is helpful, and particularly when proprioception was itself a much better generalizer than vision characteristically evolved, using the same training data. And we also noticed that when training data was limited, fewer training examples, it was much harder, it was much easier for vision to memorize, and while proprioception is still generally generalized. And so it was the movement that helped. And particularly in the V6 example, when you have 6 vertical objects right in front of the robot, we found that in all the cases, all the scaffolds, they had characteristically better or lower test error than what pure vision involved, although not as good as proprioception still, but still better than vision. And in all the cases, there was characteristically, according to a t-test, higher motion than what vision evolved. And so they were moving the blocks around and choosing to utilize its arms a lot more, and that was helping the generalization capability. But movement alone isn't enough, because we found that in one of the environments, the A8 example, that there was no characteristically different amount of motion between any of the scaffolds, vision, or proprioception. They still chose to move the objects around as much. But in 2 of the scaffolds, the most gradual scaffolds, we noticed that there was still significantly a lower testing error. And so one of the reasons we found that this was the case was using a metric called intra-category and inter-category distance. And it's the notion that you compare every object against every similar object of the same class. And we see that if we compare every small object against the final position, the final position of every other small object, we can kind of see if they're getting moved to the same positions. And if they're getting moved together or further apart. And the same thing for inter-category or between category. If we compare every small object against every big object, we see if the distances between the small and the big objects are getting pulled together or pushed further apart. So say if this value would be very high if all the small objects would be pushed to one side and all the big objects would be pushed to the other side. But what we find is that for both these metrics, they're being lower than so there's like a very faint bar here at just about 3, which means that the objects weren't moved at all. They started and ended about the same far apart. And what we find is both for intra or within category and between category or inter-category, that these objects under proprioception and the scaffolds are getting pulled to the closer final concentric positions, whereas vision-evolved controllers tended to be less pulled to the same position. So this would likely mean that vision-evolved behaviors that didn't hug, but instead hit the object and moved it with one arm over one eye, and then learned how to detect over that one eye. And so if there was an object in the bottom left, that object would stay there and never get moved off of the eye involved to, for instance, classify off of. And so as one of my committee members mentioned, it's better to hug than to hit. And for future work, I'd like to look into evolving morphology and scaffolds. I hard-coded both of these to a very simple robot design and hard-coded the scaffolds according to what I think would be helpful. If we co-evolve those two, maybe we'd reach a more optimal kind of scaffold and morphology for various classification tasks. We'd also like to examine other approaches to vision. My vision is admittedly simple, and most current systems use, like for instance, most deep neural network type image categorizers use much more complicated pictures or images like in a miniset with many thousands of pixels. And so we'd eventually like a system like that, and we'll make one. And then the final thing, which I think is like the grander purpose of this, is to perhaps evolve other cognitive building blocks. Perhaps find a way to answer the symbol grammar problem. If there's any way, for instance, a scaffold between, instead of from proprioception to vision, scaffold from proprioception to language, or hearing and speaking. Maybe there's some way to ground language using motion to kind of take the embodied approach and see if that's helpful for various intelligent agents. My code and results are on GitHub, and I'd like to thank the VACC for allowing me to use many compute core hours and the 2 National Science Foundation grants. Thank you.
So we have time for questions. So if I understood correctly, there's this fixed topology neural network, and you're changing the input that's coming in the scaffold. So it seems like that's a really confusing thing. You're getting these two very different inputs coming into the same neurons. Did you ever try having a bigger neural network with different inputs for the different sensor modalities, and that this could maybe more gracefully incorporate different sensors instead of kind of giving the same data, completely different data to the same neuron?
So I did initially. A while before I did this final result, I got this final result, I tried that. And what I found is even if you have proprioception in one set of 4 neurons, and input neurons and vision on the other set of 4, what do you give the robot? Do you give it random values for vision, or do you get 0? And we tried both, and slowly enabling one and disabling the other. And we found that the evolutionary algorithm actually had a much harder time. Might have been because of bugs in that code, but what I found it was just it wasn't working, and it just wasn't translating as well as I hoped it would. And so we then moved to a sensory scaffold over one set of inputs, and it seemed to remap the values pretty well.
So I will comment on that, because especially when you talk about making the vision more complicated, it occurred to me I almost wouldn't have called this vision. I would have thought of those like whiskers. And then you're sort of talking about 2 different kinds of proprioception, which may be why it can go from one to the other well. I don't know if that's right or not, but it seems like another way to sort of look at it. Because it does sort of feel like they've got whiskers that are feeling. No, sorry. Question?
He stole my question.
So I think it's a very interesting approach to vision and to visual learning. And I was wondering, because I don't think it's so complicated, would you be interested in building it on real robots?
Sure. Don't really have much experience with that.
Are you going in that direction or not?
So right now, I like simulating a lot, so I'm mostly focused on simulation. But if the opportunity presents itself and we're able to run evolutionary runs or find a way to evolve the brains in much faster, it would work. Because when we currently evolved this, it took a lot of computation time, and if each individual simulation takes 0.1 seconds even, it still takes a few minutes or a few hours to evolve. And so if we're trying to do this over robots, it'd be even longer, and we'd have to restart everything. And
but maybe trying to transfer.
So something like seeing if the reality gap affects this. Yeah.
Did you, in your experiments, all attempts were made with the object within range of the arms?
Yes.
Or you didn't try to put the object further away?
So all attempts to classify this were just, so there was no object classification. It was just basically a Cartesian plane of positions within grabbable distance of the robot. So and then the training was all within that range too. So I didn't look at that if the object's too far away.
Because perhaps it would be useful if the robot could learn with the object within range, but then be able see if it was able to recognize the object further away, which would give you some kind of recognition of the object.
That makes a lot of sense, and I'd like to also go in that direction, where it's essentially what we do as human beings, to see things at a distance, and so we don't like robots to do at least as good.
I apologize, I think you covered this in the beginning, but tell me again where the eyes are located.
So the eyes are located on the very center of the robot, and they kind of fan out as if it was from, I think, a monocular camera over 180 degrees. And so this is a better picture of the robot.
And it's 2 cameras?
Just one camera. And so one of the things I'd also like to go into is using binocular vision. And so if this was the center of the robot body, these rays would come out, kind of like the arms are coming out right now, in front of itself.
I think as soon as you added binocular vision and you experiment with the distance between those optical sensors, you'd start getting parallax shift, you'd start getting predator versus prey capacity. You know, with your eyes binocular, if they're on the sides, you get a very different perspective.
I played around with it a little bit in my testing, and it seemed that it definitely preferred one eye over the other, just kind of like we are right-handedness, and prefer one hand.
Excellent. So I think officially we're out of time, but of course, and certainly bug the speakers with questions they would love that, right?
Yeah.
So again, thank you.